Alright, let's get started with today's lecture then. So last week we talked a lot about dynamic program analysis, which is mainly focused on analyzing some programs by running it. This is what you've been doing the entire class, right, with GDB and whatever. Today we're going to talk about static program analysis. This can be as simple as just manually reading code or manually reverse engineering something through Ghidra. All of this is kind of static. You analyze something without running it. Today we're going to talk about some little bit more sophisticated techniques. The first one, we're going to introduce some very basic Ghidra scripting, which you can automate some things, which you'll have to do for one of the Project 6 challenges. And then we'll talk about LVM, which you can use to do some potentially more complex program analysis, or static analysis. Course information, Project 5 has been out for about a week now. I think it's due next Thursday, so in about a week now. Homework 4 is out and is due soon. I think next Tuesday or something, but should probably verify that. It's out on Gradescope. And the presentation 2 checkpoint is out as well. Any questions at this point about the projects, homeworks, whatever? Yes?
Is there any requirements for checkpoint 2 like checkpoint 1, or is it just a general update?
I would say it's about this, like very similar requirements as checkpoint 1, which is kind of what you've done since then. It's like very similar information we want though. And by now we also expect that you've at least thought a bit about what you want to do for your automated analysis part, and maybe even started it. But yeah, otherwise it's about the exact same format. Any other questions? All right. So today's content. Not okay. So let's talk about Ghidra scripting a little bit. I'm not going to go super indefinite, for 2 reasons. One, I think LVM is a bit more interesting for our purposes. And 2, I don't personally use Ghidra for scripting much, so I don't know too much about it. I usually use a different decompiler, so this is not something I'm super familiar with, but I wanted to at least introduce it so you guys can use it in your projects if you do want to. So Ghidra's API is laid out in a way where you have like a couple of, Ghidra is a Java-based tool, so everything's based kind of on classes and methods on them. So there are like a couple of very relevant classes you need to know about. Kind of like the current program, this describes like the program that is currently open. So on that you can invoke some functions like current program.getMemory.getBlocks, and using that you can, for example, get all the memory mappings that are currently listed in the process. You can use the function manager to get all the functions that the process you're analyzing has, and so on. It also has like some more specific to your current analysis window, like current location and current address, which are classes that you can use to like get like the window that is currently open under your cursor and make modifications to that. So if you're looking at a specific function, you can like use your script to like get the current address of what you're currently looking at and make modifications to that or whatever. If you want to read more about it, the API documentation is listed here. And apart from that, I'm just going to showcase how a small Ghidra script might look, a very small one in this case, but yeah. All right. So we have a few scripts here. The first one is extremely easy. It just prints out hello world. The one thing to note here is that you give it a category, which in this case I just give it a category of 300R. You do that through comments. This lets Ghidra then index it. So let's say we have like some program here. It's going to open this up in Ghidra. Right. Okay. So if we look at the functions now. All right, Ghidra's not like letting me click on anything. Okay then. Who's there? All right, so let Ghidra analyze that real quick. But if we look at the functions here, this was a very small test program. It only has like a function called f, or like a user-defined functions that does like some additions, whatever, and a function called main. And main pretty much just calls f and then prints something out. So if you want to invoke a script in Ghidra, you can go under a window and then go to the script manager. And here you can see, since we gave the script a category of 300R, will now be listed under 300R. The way you register your scripts with Ghidra is you kind of you click on this manage script directories, and then you press on the plus button, and then you can specify some directory that you want to use for your Ghidra scripts. So at the bottom here, I added the lecture that contains the scripts that the 2 example scripts. So this then kind of registers them with Ghidra, and we can just see our 2 scripts here, hello.py and Ghidra.py, under the 390R category because of the tab that was given. So now we can just press the green arrow to run the script, and this hello script is just going to execute for a second, and it's going to print hello world to the console. Very simple script, kind of just like showcases how you can actually run it. Look at the next script as well. It's a little bit more complex, but not very much. Zoom in a bit. So you can start by importing something. In this case, we have to import a source type, which is one of the classes in Ghidra. And then we can loop through all the functions. We do this by getting the current program class. From that, we can get all the get the function manager and then get all the functions, and we just iterate through that. And then for every function, we print out the function signature and the entry point, so the starting address of the function. And if we find a function that has the name of f, we set the name of the function to new name. So it's a very simple script. All of you could probably write that in like 10 minutes if you just look at the API. It's at the API documentation. And so for the hello script, we can just run it now. It's going to run the console, and as you can see, it prints out all the functions that are in this, including the address where they start. And if we now look at the main function, so function f, it's calling function uname, and the function was renamed. So Ghidra has this API that you can use, and sometimes you can use it to automate very tedious things, or you can automate some useful things for your analysis. This could be, for example, while you're reverse engineering some device or some software, you realize there's like some logging function that's a lot of functions use to like log some error messages, like print like some debug print or whatever, and then you might recognize that this could be relevant to like your reverse engineering, like if like some function that is in charge of handling some registry entries or whatever prints out error writing to registry, then you could, for example, use that to name the function and give it a name that's related to like registry or like registry writing or whatever, and you can just manually script it out, like every function that calls a log, get the string that it uses and just rename it to that. There's a lot of things you can do. It's a very simple example. So yeah, if you're doing something on a closed source and want to do some form of like analysis, Ghidra could be useful for that. But yeah, it's a very simple example. So if anyone have any questions on this? Yeah.
If we wrote like a lot of Ghidra scripts or something, would that count for our automatic portion of the
Yes.
thing? Okay.
You probably want like more complex scripts than the ones that's shown here. You can, for example, write scripts that do some form of data flow analysis from like some source to some sink or so on. There's like a lot of interesting things you could do, or it depends kind of like a lot on what you're doing, what you might want to script out. But yes, that definitely would count. Okay. Any other questions? All right, let's move on to the rest of the lecture then, and that will be focused on LVM. So I briefly mentioned LVM a couple of times throughout this course now. It's the compiler backend that's used by a lot of languages, which include like C, C++, Rust, Swift. All of these are based on the LVM compiler backend. So we talked a bit about like kind of the compiler pipelines before in previous lectures, and how when you compile code, there's the front end where you kind of have like your source code, which could be in C, C++, whatever. This is then usually parsed to some abstract syntax tree, and then this abstract syntax tree is then parsed to like some intermediate representation. And this is kind of the level where LVM starts. So you have your front end for a language, which could, for example, for C and C++, you might be using Clang. For Swift, you might be using Swift compiler, whatever. They all parse the source code in some way and generate this LVMIR at this point. C also has like GCC and other compilers that aren't based on LVM, but Clang, for example, is. And so this then gets parsed to LVMIR, and at this point, LVM starts and handles the rest of it. So LVM has like its own front end, which is kind of the LVMIR, and at this point, it kind of does optimizations, all of that stuff, and this is kind of the phase that we care about for this. And after the optimizations is done, this IR can then be converted into various architectures like x86, MIPS, ARM, whatever. This is architecture agnostic, so it can then compile to all these architectures that embedded devices, desktops, whatever are using. So, yeah. If you would, for example, want to write your own programming language, and you might not want to like write all of this on your own, especially if you want it to actually be usable and fast, you don't want to like implement all of your own optimizations. One thing you might do is just writing your own source parser that generates this LLVM IR, and then you can just use LLVM to have like a very optimized build that supports like ARM, x86, all these architectures without having to like deal with this yourself. It can kind of be plugged into like existing compilers, and that's exactly what's done in the real world, like a lot. So in this course, we're gonna learn how you can basically interact with this IR to make modifications directly to it. So it's not like some toy tool that we play around with, it's something that's actually being used. And if you took an advanced compiler course, you might also deal with LLVM a good bit, because it can kind of be used in a good way to write your own optimization passes. All of LLVM is also open source, so you can read all the optimizations that the compiler does as well, like understand them on a practical level, and just very useful for this. Any questions so far? Okay, so let's talk about what we'll be using it for. So LLVM itself is built in a very modular fashion. So once you get to this IR stage, the way the optimizations work pretty much is that you have a lot of independent passes. So you have your IR, and then you invoke some pass on it. Let's say, so here's pass 1. And then pass 1 does some stuff to the IR. Maybe there's probably some optimization pass, for example, and maybe it makes some modifications to the IR that makes a loops a bit faster, like some form of a loop makes it faster, or like some mathematical operation, whatever. And this then spits out IR again, in the exact same format as the previous one was, just with the optimizations applied to it now. And then pass 2 comes in, runs again, and once again, pass 2 is just going to spit out the IR again. And this, for example, could be a security pass. Maybe this is the pass that modifies the code to include the canary stack overflow checks. So all of these are kind of just done through compiler passes, and LLVM has hundreds of these that run one after another to like do these optimizations. And after each pass, this IR is just emitted again and then passed on to the next pass. So it's very modular. This means that we can write our own pass and just put it anywhere in this pipeline. So in this location, we can just throw in our pass, and our pass might modify the code in some way that we care about, or this could, for example, be ASAN, the adder sanitizer. You could write an ASAN pass. This would be injected here, and then your pass modifies the IR, spits out IR again, and then this just gets passed on to the next passes of LLVM. So it's kind of very modular in a fashion where you can just go into the middle of it, make your changes, and it just keeps working. So on the bug finding side, LLVM expose,
Is it possible for like a later pass to undo work that was done by like a previous pass?
Yes,
Okay.
absolutely. So sometimes passes also run multiple times, especially with some that's very important. There's, for example, one thing in compiler optimization is called inlining, which you might have heard of, is if you have function A that calls function B, and function B is a small function, you might just remove this function call and place the instructions from B right like in the middle of the A function. So basically inline. And this form of inlining is something that makes a lot of, the main reason it's done is, yes, you remove the call instruction and the ret instruction, which is like, okay, that does something, and like the way you don't need to set up a new stack frame, whatever. But mainly it makes a lot of optimizations a lot easier, because a lot of optimization are done at the function level. So let's say you do some optimizations and then you like perform the inlining, and then maybe you can suddenly do like even more optimizations. There's like a lot of like constant propagations going on. Don't want to cover like too much of it, but yes, that does happen a lot. Like something is passed around multiple times to like keep optimizing it, right? Something changes and then you can run it again and like it changes something else, and so on. All right. So on the bug finding side, LLVM gives you this IR. And this means that you have a view of the entire program, and you can programmatically very easily modify it. So you don't need to so if you want to manually analyze a code base, you don't need to write your own parser that parses the C code into like a machine representation for you, so you can like print out all the functions. So you don't need to like parse all that out yourself. you can just write an LLVM pass and you can operate directly on this IR and you have all the information available to you. This makes it very powerful. So we spoke a bit about, for example, data flow analysis, where you might want to, for example, for a heap bug, you might want to measure if like a free is called on like some memory and it's called again on that same memory again later to like find a double free bug. Using LLVM IR, you might be able to do that because you can see all the function call that a function makes. You might be able to like map one function call, like say that it's like being done again at a later point, and this makes it extremely powerful. Yeah, and so it's kind of like why not source? If you want to do LLVM scripting, you do need source code because LLVM is a compiler pass. So this IR is pretty much only generated if you have source code available that you can parse into, that you can give to Clang, and Clang is going to generate this IR for you. There are tools now that you can give a binary and it's going to generate LLVM IR from that binary. But those are still very new, somewhat experimental, but they have been in development for a bit now. Any questions? All right. So it's a very brief introduction to how LLVM actually looks. So it's completely open source. It's hosted at the LLVM project repo. You have the Clang compiler here, which is the front end that can be used for C and C++ that basically generates these abstract syntax trees and the IR initially. You have libc, which is a C standard library implementation that they use. And you actually have the LLVM project /LLVM, which is the actual LLVM compiler backend source code. If you want to build LLVM, you can do it yourself as well. For the project, we're just going to recommend to do a sudo apt install on it. The instructions are in the project. Building gets messy. If you try doing a debug build, it's going to take like 30 gigs of memory and 40 gigs of disk space once it's done compiling, and it's completely massive, and my laptop doesn't handle it very well. Yeah.
I would like to put some input into this. It took me 2 days to build LLVM with my laptop, so don't try it.
Yeah, the code base is massive. But yeah, that's kind of what goes into like compiler optimizations. There's a lot that goes into it. The code base is completely massive. It does so much to make your C code this fast, which is kind of insane if you think about it. But yeah, so you could build it. If you do build it, build a release build, not a debug build. Release builds are fairly reasonable to build. Still takes a while and still takes a good bit of space, but not nearly as much as a debug build. So if you want to become an actual LLVM developer or debug some more complex, so like a pretty complex pass that you're maybe writing even, you might want to compile it yourself so you can, for example, turn on the assertions and stuff like that, which makes debugging your pass a lot easier. But yeah, just like a brief introduction to the source if you do want to look into it more. Also, as I mentioned earlier, all the LLVM passes that your compiler runs are open source. So if you do decide to use LLVM for your like automated analysis part of your presentation, make sure you look at some of those passes, even if their optimization path potential might not be super relevant to what you're doing. But you kind of get a feel of like how these paths are built, how the syntax of the API looks, and so on. And obviously, they'll have like very extensive documentation for it. Okay, so basic compiler pipeline, where you talked a bit about it there. We have your program, and Clang basically is going to take your source code, put it in an AST, and generate this LLVM IR. And then this is going to be moved to like some DAG graph, and going to be lowered to like LLVM machine IR, and eventually you'll have like your assembly. We don't care about this part at all, and we don't really care about this part here at all. For either. For a lot of static analysis, you will also be working on an AST, because that's also a very powerful graph at times. But with LLVM, we're mainly going to be sitting in this kind of area where we write our passes, where the IR is generated for us, and we can just write our passes to interact on the IR. This is what we are going to be what we care about pretty much. So let's look at a demo here of how this IR actually looks. So if we look at the program here, this is the same program that we looked at in Gitter earlier. We have our main function, which just calls hello from main, and then prints out what the function returns, and in F just does some simple comparisons, whatever. So let's look at our makefile a bit, because this is in this case a little bit interesting. So we're going to use Clang in this case, Clang 14. This is what you'll be using for your projects as well, although all the other Clangs and whatever should work too. To emit the LLVM bitcode file. So you can pass some flags to Clang, the minus emit LVM and so on, and point it at the program. And then instead of compiling it into a binary, it's going to compile it into this .bc file. And just run the make command. And now we have this program.bc file, which is not in human readable form, it's in machine readable form. So this is what the compiler would internally use to kind of like make its modifications, parse it out, and so on. Next, we continue looking at our make file. We're going to use LVM minus this. This is kind of their disassembler, which you can use on this .bc file, and it's going to give you a program.ll, which is the human readable form of this. And then finally, we're going to compile it into an actual binary. For this, we'll use a linker. So this is going to basically generate the object file for us, and then we're going to link it all together into the final program. This is kind of like what would run if you didn't like do this emit minus LVM and just like ran Clang 14 on like the program.c. It would then also finally emit the program at the end. Now we just kind of separate it into a few more steps, so we have like a few of the intermediary files so we can now look at. It's also worth noting the minus f no discard value names flag. When you're actually looking at the LVM bit code, by default, LVM is going to strip a lot of the information from the source code at this point. If you keep this flag on, more of the source code, like variable names and so on, are going to be maintained, which makes reading it a lot more pleasant, I would say. Okay, so let's actually look at the code now. Well, it's a human readable version. If you consider this human readable or not is kind of up to you, but it's at least somewhat readable. So starting at the top, we can see our source code file names listed. Then it talks a bit about the data layout. This kind of describes how big are pointers, how big are integers, which kind of going to depend on the target machine. So if you're using x86, 32-bit, or 64-bit Linux, the pointer size is going to vary, for example. So this is kind of what's encoded in this long string here. The target triple, we're writing to x86, 64 on Linux. And scroll down a bit. And here's our main function. So you can see that here we define a function. This function returns an i32. And then we can look at the actual code for the function. So it has a couple of instructions here. It allocates some place on the stack for a variable. Then it calls the f function, which with an integer argument of 3. And the result is then stored in call. And then it calls the printf function. And as arguments, printf then takes some element pointer called .string. If you look up there, top .string is the hello from main %d string. And it also takes as an argument the call that was returned from f. So this kind of like demonstrates like everything in the program just encoded in LVM's IR. The same for function f. We scroll up a bit. We have our, it takes like the argument of an i32. And then we can see does some allocations again, it stores some things, does a subtract operation here, stores some more things to memory, has a comparison here where it compares the %1 variable, which is here, using a constant of 2. If you look back at the code, you can see that this is the variable and it's comparing it to a 2, and so on. This is basically just encoding the program in the side of this IR, and this is encoded in a control flow graph. So you have so for this function, for example, you have your first block, and then you have these other blocks, and it's like from this if statement can either jump to this block or it can jump to this block, and then both of these are then going to branch to the end block here at the end. All of this is also in SSA notation, so single static assignment. So no variable is assigned twice. Not sure if there's a good example of this here. Let's look at the source code real quick, where that may be relevant. Okay, so b is assigned to 0 and then b is assigned to 5. Let's see where this was happening. Yeah. So here's a store that writes 5 to b. Where's 0 stored to b? Okay, it looks like in this case, since it's just doing a store operation, not actually writing to b in terms of LVM semantics, it doesn't actually create a new SSA variable for it. But pretty much everything, like every internal assignment Like for example, these here where it's like %1, %1 is like everything with a percent sign is a variable name in this case, and all these are going to be in single static assignment form. This specific code does not seem to have any good examples of it, but you'll probably notice it once you start working more with it that this will become very relevant for a lot of things you do. So any questions on this so far? All right. Let's talk a bit more about the IR and how everything is constructed when you start writing your passes and how everything looks pretty much. So as noted earlier, the format on which LVM operates is referred to as the bitcode, and use the BC extension when you generate it yourself. And as noted earlier, like the instruction also just machine independent assembly. So you can the LVM IR can compile to x86, ARM, whatever. All variables are in SSA form, which I should have probably had a better example of but you can just believe me on that for now. And then when you start interacting with LVM as well, everything is kind of split up into this CFG style form as well. So you have your modules. So when you compile a larger project, you're going to have like individual modules for it that kind of combine together to make this project, which the linker is going to link together. So LVM has that too, where it splits everything up into modules. And each module then contains the global variables and the functions for this module. And then you have the functions, and then all the functions have basic blocks, and all the basic blocks have instructions. So it's kind of the similar kind of control flow graph situation where you have functions, each one has base blocks, each one has instructions. So when you're writing the pass, you can kind of iterate through them. You can, for example, say, loop through all the function in the module and print out the function name, or give me all the instructions, and so on. Inside of the LVM source code, all of these are represented as C++ classes. So you can make it very comfortable to use them in this regard. You can look at a few more specific instructions for LVM. So we have, for example, the subtract operation, which you pass some arguments, and you can say in this case that from variable 0 you subtract 3, and it's going to be a 32-bit integer register, and the result is going to be stored in %sum. You have a compare instruction where you compare a variable that's stored in %1 with 2. You have memory operations. So memory operations are kind of they're kind of just defined by like the store and load instructions. So in this case, you're storing the value 5, which is an I32, to %b, which is a memory location in this case, and it's a line on a 4-byte boundary. It's also a control flow, which, for example, could be based on like branch instruction on a compare, where if you can either go to the if.then branch or the if.else branch, which you could kind of see in the IR example we pulled up earlier, where based on where it does the compare instruction, and based on this comparison, it branches either if.then or if.else. There's also casting, so in this case, it's truncating the integer 950 to an I8, so it's going from a 32-bit integer to an 8-bit integer. And there's also like some other instructions, like the alloc A instruction, which is kind of used to make room on the stack, for example.
On the example, there was also if.end also?
Yeah, so this is kind of how it encoded like the if block in this case, where you have the if.then, which for an if statement is like the if it's true case, the else case, if else, and then the if.end they kind of just use to name like at the end like both branches come back together to the if.end.
Oh, within the block.
Yeah, or within the function. So you have like 4 different blocks, like the first block, second block, third block, and the fourth block.
Okay.
But yeah, so you can kind of think of it, kind of if you have like, here's the if statement in the first block, then you have like your 2 branching blocks, which could be like the then and the else, and then both of them come back together for the end here. Okay. Any other questions? Okay. So, yeah, talked a bit about this before, but the reason why we care about LVM for security research is kind of the modular design that it does offer us. So this means we can kind of run our own pass and run it with it. And the logic of these passes is kept completely isolated. So all of these can kind of work independently of each other, which makes it very easy to kind of keep extending LLVM with your own passes, whatever you're interested in. And yeah, we already talked about everything else here. So let's talk a bit about how you can actually write these passes. So this lecture is labeled static analysis, but LLVM can be used for both static and dynamic analysis. So in terms of static, you have a lot of control. So it gives you the IR, and then it gives you a very powerful API on top of it that you can use. So you have access to the entire source code through these modules, the functions, the blocks, the instructions, and you can basically analyze everything about it programmatically. This enables you to do a lot of static analysis, but LLVM also lets you modify the IR and then recompile them to a final binary. So you can also use it for dynamic analysis. It can be used for both in this sense. So the dynamic analysis can be very useful sometimes, and that's kind of what you're going to be doing for your project as well in terms of this, where you can, for example, say, for every single fgets call, I want to add a check before it that checks if the size is correct, or like an assertion before to make sure that the size isn't too big. And you could, for example, use that while fuzzing, and then you have an assertion error that if it's caused, you can find more crashes. It's kind of what ASAN does, for example. With static analysis, you can instead just implement various algorithms that have been researched to like do some form of bug hunting on code. This could be, for example, to look through every function in the module and see if any of the functions call printf, and if they do call printf, verify that it's not being called with like a variable that the user might control, or anything of that sort. You can kind of implement all these algorithms inside of statically on this IR. We didn't talk much about this in general in this class, because static analysis and data flow analysis and these topics are incredibly complex, and I believe that would kind of take an entire course on itself to teach. So it's not something we really cover here. It's also kind of deeply theoretical, where you kind of build up upon a lot of like the concepts you learn in 311 and 250. So it's not kind of what we're going to be focusing on here. So we do a bit of static analysis, and some of them are very easy to do. There are a lot of algorithms you can do to find some very low-hanging fruit bugs. But in general, static analysis quickly becomes a lot of effort for things that are hard to find. Like if you want to write something that can find all double frees, it suddenly becomes very hard with especially with pointers. So let's say you allocate a memory region. So you allocate X. Maybe you pass X into a function. Maybe you have like a different reference to X, and maybe X is even part of a struct. So X is then used in the various different places in your code. So X is not just X anymore, it's X and like all the other locations that reference, like other variables that reference the exact same memory location. So now it might be very easy to find like if X is freed and then like later X is freed again. So you could say this is a very easy bug to find, and you could probably script that out if you're familiar with LLVM in less than half an hour. But now what if one of these references is freed? Well, that would be the same bug, but now it gets a lot harder to find. What if one of these references was passed in a different thread and that thread made another 10 references of it? What if one of those is free? And suddenly static analysis becomes a very hard problem where you, especially because you also need to be careful about like how stuff scales, and it becomes very difficult to do well and correctly. That's kind of why we also talk about how static analysis often has the issue where it can kind of give you a lot of bugs or a lot of potential bugs with like a confidence score, but it's almost never going to be able to 100% tell you this is a bug, unlike dynamic analysis, like fuzzing, for example, where the process crashed, so you know there's a bug. With static analysis, kind of like, this looks like something that might be a dangerous pattern that could be a bug. Look into this more manually. That's kind of where static analysis usually ends up nowadays. In the terms of VR, at least. So, yeah. Okay, is that everything on the slide? Pretty much. Are there any questions on this? Okay. So now on this topic, we're going to just have some more demos. So let's start looking at some actual LLVM passes, how these look, and what they might be able to do. clean this up real quick. Let's go to- Okay, so we have the exact same program again as before. Just print out the stuff. We got makefile again. Does a bit more in this case. So we also have our path in this case. So we create a build directory for the path. Go there. We're going to call cmake, which is going to basically make the stuff that's in the analysis path. Once again, we're going to emit LVM for the target. Then we're going to call opt, which is a binary that comes with LVM, it's kind of the optimizer. And then you can tell it to load a pass plugin, and we can give it kind of the pass plugin directory and then the name for the plugin, and we can tell it what to operate on. And then it's going to compile the LVM bitcode into an ELF executable. And finally, we can also emit the human readable bitcode for it. So it kind of does what the other one did, just in addition to that, now also compiles our path and applies the path we wrote to the target binary. So let's start looking at the actual paths. Actually, just easier. All right. So there's a good. So all of this is pretty much just boilerplate code that you're going to just be copy pasting. There's nothing you need to remember or anything at all. So let's start at the very bottom here. We basically just tell that we register a function that LVM can call to get some information about this plugin. It's kind of all it does, and it's completely generic. You kind of just copy paste it. Then you have the get analysis plugin info. This is the function that this here registers, and this kind of just describes some things about the path. For example, it gives the LVM version that's being used for the API here. It's going to give the name of the path, which in this case is just analysis path. You're pretty much just going to add it to LVMs like paths. And you're also saying that this is a path that is being run on modules. It's all very generic, and you understand this. You kind of just copy paste that and modify the names and so on. So we don't really care about that yet. So this is kind of when it gets interesting. So here we start defining the main struct for the path. So this is the main entry point. As mentioned earlier, down here we specified that this is a module path. So when we started earlier, how LVM has modules, globals, functions, so on. With this, you can specify what this path is being run on. So you can write a path that gets called for every module, for example, or you can write a path that gets called for every single function, or one that gets called for every single instruction. It's kind of how, when we talk about pin, you can register hooks for like instructions, blocks, functions, whatever. You can do the same here. In this case, it's a module path. And we just call the visitor function in this case, and pass the module to this function. And this visitor function is the one that we wrote for this. Finally, we also return a statement here, and this statement, the preserved analysis, all kind of just says that our path did not make any changes to the IR. So LVM can kind of optimize around that. Otherwise, if we need to take some considerations there. And we also register the is required method inside of true. So this module is going to be called for every module pretty much, and it's never going to be skipped. Does all of this make sense so far? It's kind of mostly just boilerplate, like registering our plugin and saying this will be run in every module. So let's look at the actual code now. This is kind of everything we have to write for this module. So we have our visitor class, and it takes as an argument a module. So this path is being executed at compile time, just to be clear. So when you're compiling, in our makefile, when we run this line in our makefile, the /bin/opt or the opt binary, this executes our path onto the IR during the compilation process. So it's not something that's executed while the binary is running. This is something that's being executed while the binary is being compiled. So at this point, we can kind of just use some of C++ niceties and kind of like have like these iterators and so on. So first we print out hit, just as like a debug print, I guess. And then we can loop through all the functions in the module, and then through all the blocks in the function, and then through all the instructions in the block. And during that, we print out the function name and the instruction. So this is a very simple path, where during compilation, we're going to loop through all the functions we're compiling, print out their names, And for every function, we're going to loop through all the instructions and also print out their names. All this make sense so far? All right, so when we start our compilation, what would you expect to happen then? So when we compile and then when we run the binary, what would you expect to be different than when we would compile it normally? Yeah.
You're gonna see all the function names in the assembly.
Yes, is this going to happen while we're compiling or when you run it?
While you compile, like when you make it.
Yes, exactly. So as soon as we type make, all this should be printed out. So let's give this a go. I'm going to run main. It's going to do some stuff, compile like all the other stuff first. Now it's currently building our pass. So here it started building our pass then. And here you can see that it started printing things out. So it went through all the functions in the module we passed it, which was the main function and the f function. First it prints out the debug print we left in, then print out the hit. And then it looks like it got to the f function first in the iterator. So it printed out the function name, which was just f. And then all the LLVM IR instructions it printed out as well. So if you remember, we're writing this pass at this location here. So we have the IR, and that's what we're all printing on. So when we tell it to print out all the instructions, we're going to get the IR instructions. So for function f, we now print it out that these are all the instructions inside of this function. Made it the same for main, and printed everything out. So all of this makes sense. Or does anyone have questions on this small sample pass? Okay, and let's look at another pass now, and this time we're going to do something a bit more interesting, and we're actually going to modify the IR. So the program that is compiled at the end is going to be different than the program that you pass in as source code. So the program, once again, it's the exact same. And let's go to demo 2. Here where we didn't modify the program, we can run it, and it's just going to print out hello from main 5, because that's like what passed the if check. So if a is bigger than 2, which a is not, it's going to print out 5. So let's just clean this directory up real quick and give it 3. Right, so our program is the exact same. So you would expect if we make this, finish building. This time it didn't print anything out because we didn't tell the pass to print stuff out. And we run instrumented. Now it prints out 3. This is because we modified the program during compilation using our pass. There's also, I believe, I left the initial program intact here without instrumentation. And this one you can see still prints out 5. So the source code is still the same, but we modified it inside of the pass. So let's look at the actual analysis pass then. So we once again have this same type of boilerplate where we specify that we run this on an entire module. You can also run this on a function, which oftentimes is better. But for this case, running it on a module is perfectly fine for us. Some more boilerplate code. And we're going to tell once again to call the visitor function for every module. So let's go up and start looking at the visitor function. So this is what does the actual work again of the pass. So let's talk a bit more. One more thing to note about LLVM is that in terms of the C++ code base, everything is a value. So value is like one of the structs they define. So everything you kind of get, like every function, every register, every value, they're all kind of listed under this type of value as well. So for a lot of things, so pretty much anything, you can just cast to a value when you're writing your pass and operate on it that way, which is often very useful. So first of all, at the top, we're going to define a vector of instructions. So instructions is another type in LLVM, which defines like any of the instructions. And then we're going to loop through through every function in the module, and through every block in the function, and then for every instruction in the block. So for this part itself, we could have just written an instruction pass and did this as well. Although there's some more in this as well later and further, which I wanted the entire module. That's why we made a module pass. Then we have this statement, which looks a bit weird, but this is kind of how you do the matches in LLVM to figure out what type an instruction is, or if you search for a specific type. So we go through all the instructions, and we try casting it to a binary operator. If it is, we execute this. If it's not, we ignore it. So this is how you basically do it in LLVM using the dim cast to binary operator. If it succeeds, you keep going. If not, you don't. So in this case, we execute this only when we have a binary operator. And then we check the opcode of the instruction and verify and check if this is a binary operator for the subtract operation. So what this loop's basically doing is we go through all the functions, all the instructions in every function, and we look for every instruction that's a subtract instruction. If not, we just continue and move on. So once we found a subtract instruction, we register an IR builder. This is an object that basically lets us create new IR instructions. And I'm just going to preface real quick. The goal of this pass is to replace every subtract instruction in it with an add instruction. It's a very simple purpose and wouldn't go well with a real program. You probably would not want to do that if you want to keep the functionality of a program intact. But that's our goal with this program. So we're going to look for every subtract instruction first of all, and at this point we found a subtract instruction. So what we do is we create this builder on the current instruction we're on. Then we're going to get the left-hand side of the current instruction. We're going to get the right-hand side. So we're going to get the operand 0 and operand 1, which is going to be both like the left and right of the subtraction. So if you're doing 5 minus 2, this would point to the value 5, and this would point to the value 2. And then we're going to create a new instruction using the builder. And we're going to create an add instruction using the left-hand side and the right-hand side. So we just created an instruction that basically adds LHS to right data, or RHS. So at this point, we already created inside of the IR this new instruction, this add instruction, which we wanted to add. Now we have the issue that we have both the add instruction and the sub instruction in the IR, and we don't want that. We wanted to replace the sub instruction. So now we have two more steps. First of all, we need to delete this sub instruction, but it's unfortunately not that simple. So if we look at the IR that was generated real quick, I don't think instrumental. Sure. So if you look at the instructions, all of these kind of have like a return value. So if we see, for example, where's an add or sub instruction? Okay, there's the add instruction, for example. This is already after it's been introduced, or already replaced it. But if you see, the add instruction has a return value to %6. If we add a new instruction right here, this would then write to a different variable that isn't %6. So if we now remove this instruction, then the later instructions operate on %6 would fail, because they expect this variable to exist, but instead you just added a new instruction that points to a different variable. So you can't do that, because like this %6 has like uses later in the module, and they're then going to fail, and the compilation is going to fail, and LLVM is going to print a really mad error message out at you. So what we need to do in our pass here is that we go through all the use cases of this operand. So we have this subtract instruction, it returns something, and then we go through every instance we loop through that uses this variable in the future. And we're going to get this user, and then we're going to replace the operand that it acts on from the one that was used by the sub instruction to the one that is now being used by the add instruction. So if you have like a sequence of x1 equals old instruction, and then later somewhere in the code, x1 is like, there's some, say, x3 is equal to x1 plus 5. This is one of the uses of x1. And now we insert a new instruction here. Let's say this one says a1 is equal to new instruction. With the loop, we're basically going to find all the instances where x1 is used, and then we're going to replace the operand with the operand of A1, so this X1 would then be replaced to A1, and now we can happily delete this one because the X1 is no longer used anywhere. So we have to do that at this point. That's kind of what this thing does. And then we push the initial subtract operand to the delete array vector we initialized earlier up at the top here. And finally, at the very end, after we've looped through all the instructions, we just go through the delete array and remove all of these instructions that we just replaced. So the reason we do this, this is just done by using i/erase from parent, where you just erase the instruction from the block class. The reason we do this at the end, while looping through here in this way, instead of doing it like right here and just deleting the operand, is because we're still inside of this iterator here, where we're looping through everything. And if you were to delete an instruction while looping through the instructions, that would break the iterator and your loops would stop working. That's actually something I had to debug for a bit when I was writing this pass initially. So I just pushed into a vector and deleted at the end. But yeah, so this is what the pass does. In theory, it's pretty simple. In practice, there are some things to consider, where if you're writing LVM passes, there's a lot of very simple mistakes you can make that suddenly break compilation. It's like everything needs to be SSA. If you create a variable is used and you delete the variable, you should be sure that all the next users no longer use it. All these small mistakes can break compilation. Also, in addition to that, if you remember for the last path where we didn't modify the IR, we returned preserved analysis all and basically told LVM this pass does not modify IR. In this case, we need to give it something else, such as preserved analysis none. So LVM does not try to, or doesn't think that we didn't modify the IR, because then it might optimize it to some other pass and doesn't realize that we modified the IR. So yeah, in your project, you are going to be writing an LVM pass. In your case, it's going to be a fairly interesting one, I think, where given a function, you're going to find all calls to malloc, and you're going to retrieve the size that malloc is being called with, and then you're going to find I think either an fgets or a string copy, some functions like this. You're going to find a function of that sort, and see if x is one of the arguments in here, and if so, you're going to check if the size is bigger or smaller to it, and insert a dynamic check in here that's going to perform a size check. So you're going to basically write a pass that dynamically checks if the size is correct, and it's going to spit out an error if it's not. So basically write your own little ASAN implementation for a very specific case. But yeah, any questions on this type of stuff? All right. Then for this class, I thought maybe we'd review homework 3. I believe a couple of people struggled with that, so we're just going to look through the answers real quick. And yeah, and if you have any other questions, feel free to ask them as well. I'm going to quickly disconnect so I don't accidentally leak student grades or whatever when I go on Gradescope to look at this. But yeah, if anyone has any question related to the course, now is a good time. We have 15 minutes left, and we're only going to go over the homework, so no rush today.
It's not too late to start the extra credit assignment, right?
No, but let us know soon what you want to do. Yeah, you're still good. Yeah.
What are the use cases for LLVM versus something like Binary Ninja for scripting?
So Binary Ninja and these types of tools, they have the advantage that they work on closed source code. So they're kind of like decompilers, so they work very well on binaries given the information they're given. LLVM has the advantage that it has a lot more information because it works at the source code level. So it kind of knows everything about the code. It knows exactly where functions start, where functions end. It also has very powerful API instead of everything is SSA, which Binary Ninja has as well. Binary Ninja's API is also extremely powerful, but a couple of things kind of get lost through the compilation process. So the advantage are kind of that LLVM is kind of better if you have source code and like can inject yourself into the compilation pipeline. If you don't, there are like all these decompiler alternatives. LLVM is also extremely good to kind of build upon if you want to write your own extensive tooling. So there's a security company called Trail of Bits, and one of their people there had a very interesting project a while ago where they tried to do fuzzing using GPUs instead of CPUs. So for those that might not be aware, GPUs have like an entirely different architecture, so you can't just take x86 instructions and run them on a GPU, but that's kind of what they wanted to do. So what the people did there pretty much is they wrote LLVM code that for a given binary, it transforms these instructions from the x86 code to GPU instructions that do something very similar. So that's, for example, where they built an entire tool upon using LLVM to like take this IR and then translate all these IR instructions into like GPU instructions instead. And with it, they were able to run, like, for example, your x86 binaries on a GPU and could see if fuzzing through that would speed it up rather than like using the CPU. So like projects like that, or like ASAN, where you want to instrument a lot of code. Like LLVM is really good, especially if you need to modify the code. If you do purely static analysis, want to only do analysis, LLVM is still really good because its API is extremely powerful and it has a lot of data flow analysis information already encoded into it. Like, for example, the thing, like the loop we did, where I still have it open, like this small loop here, where you go through all uses of a variable, is already something that's extremely useful to have in an engine, where you can just like give it an arbitrary variable and give me every location where this is used in some operation. Like having this ability and like being able to use it for this lets you do some very powerful analysis sometimes. That makes sense. Any other questions? Okay. For the homework, so let's quickly go through this. So it's question 1. I ended up removing it and giving you the answer on Campsfire. I hope everyone saw that. I decided to remove it because it's not super relevant, and I think I only very briefly mentioned it in the lecture once. But yeah, the question kind of the chunk pointer internal used by malloc points directly to user data. The answer was false because if you have like a chunk here, and then that's the correct way. If you have like a chunk here, and then your user data is in this region, but the internal malloc pointer is going to point to like up here instead of the user data down here. So that's kind of the question, but not very relevant, and probably shouldn't be on the quiz. Question 2. So, how does malloc know when a chunk is not from the main arena? Does anyone want to try explain it? Or, okay, there's not much to explain, but yeah, it's just a flag there that's being set. So malloc just checks the flag and goes based off of that. Let's see if I can. Okay. Who wants to get an answer to your question 3? So why do we bother with all these free lists? Couldn't we instead just mmap everything? Like, what are some reasons why we do that? Yeah.
It depends on the OS, but sometimes mmap can only give you a specific or a multiple, like a page size or something like that.
Yeah, that's a very good reason. For example,
I want like 4,000 bytes for an 8-byte struct.
Yeah, that's good. Also, just general performance, mmap is an entire syscall. With a free list, you don't need to do a syscall for every allocation. But yeah, also like the allocation size, like a lot of reasons. Mainly boil down to performance, but yeah, that's pretty much the answer we're looking here for that. Given that the top chunk has RX300 listed as a size field, what would happen if we make 2 allocations, each which with size RX200, assuming all the lists are empty? Who wants to give that one a go? So just to kind of draw this out, so we have our heap here. Bottom, we have a top chunk, size 0x300, and we try making 2 allocations of size 0x200. What would happen here? Yes.
So the first one just gets allocated from the top chunk.
Yeah. So we do the first allocation. It's going to move the top chunk down, and now this is of size 0x100.
So then the second one's going to have to do a syscall and have the kernel grow the size of the heap region. And if the heap region is at max size, then it has to create a new heap region elsewhere.
Yes, exactly. So the size is going to be made larger, another syscall is being made, and then you can once again just do it, grow it as normal again. Correct. And if anyone has like questions about this or anything else, you can also just ask at any time. Question 5. Describe how our chunks are allocated from the fast bins and explain under which circumstances the fast bins would be the choice for an allocation and how the FD pointer will be used to unlink a chunk. Who wants to give that one a go?
So fast bins are last in, first out. So once something of a small size, usually like 16 bytes is deallocated, it goes to the fast bins. And then that size is kind of, instead of just being freed completely, it kind of stays there until until the program needs another size of 16 bytes, at which point it takes the last in, first out. So it'll take that same fast bin and allocate that exact same region of memory to whatever variable is allocated.
Yeah, pretty much. And to extend on that, it's kind of like maintains them inside of this linked list structure, so it also has like the FP pointers to kind of figure out where the next fast bin is. But yeah, that's generally what we're looking for here. Also, maybe to note that if Tcaches are in the picture, the Tcache will be checked before the fast bins. But yeah. How are allocations from the unsorted been made?
It checks the unsorted bin after the fast bins, or like if it don't have the size that would go on the fast bins, and everything in the unsorted bins will either go into small bins or large bins, but it hasn't been sorted yet. So it'll loop through until it finds one that's a big enough size to give the allocation you want. And anything that it encounters that isn't the right size, it'll sort to either small bin or large bin, depending on the size of it.
Yeah, exactly. That's good. Okay, let's move on to question 7. Spot the vulnerability in this code snippet. Yeah, hopefully no one just thought and I spoke too far. Who wants to give this one a go? Yeah.
Line 8, the use after free vulnerability has, if you free the pointer, but then you again start accessing it at line 8.
Yeah. So we allocate the pointer here, and then if an error occurs, like if the error variable set, which somewhere in the code happened, the free pointer, the pointer is freed, and then this operation will once again reuse the pointer, so we have a use after free here. Or did you say use after free or double free?
Use after.
Okay, yeah, exactly that. Make sense to everyone? Okay, let's move on to the next one. Oh, it's just the example answer anyway, so wouldn't have given it away. All right, another code snippet. Is this big enough for everyone to read, or should I pull the image up on a second screen, or like a different tab? Good. Like, who wants to give this one a go? Yeah.
So double free if the switch case hits the default, and then after it'll free again.
Yeah, exactly. So we have the read data function. It does some operations that we really don't need to care about, except the one here where it allocates the data variable. Then it has a switch case. If none of these cases are met, the default case is invoked. Here the data is freed. And right after the switch case, the data is freed again. So we have a double free bug here. All right. Then question 9, is that the last one? Yeah, so last question. Okay, now zooming in did not work. All right, okay, I'm just gonna hope this is readable for at least most of the class. Who wants to give this one a go?
If you hover over it, you can screen it right here.
I can probably.
No, you can, if you hover over the image, I think you can.
Oh, this thing, yeah, good point. Didn't see that. All right. Who wants to give this a go, finding the bug? Someone who hasn't answered before, if possible? Yeah.
There's a use after free on the second to last line. If n is less than 0, then the condition will be true and string will be freed. Then on the second to last line, you string at blank, meaning that's it.
So you mean that on line 11 it's freed and then it's used again here?
Yeah.
That's actually not the case, because right after the free it's going to return.
Okay.
So this is not a bug in this case. There's a different bug though. Yeah.
In line 5, I think length could be int max. So then in line 6 it will become 0.
Yeah.
Malloc could be called as 0. And then you'll have a heap also all throughout the loop, essentially.
Yeah, perfect. So in this case, it's not a heap bug specifically. It's kind of just an integer overflow again, where the length variable can overflow here. And if that happens, the loop is going to loop through. The length is going to be massive, but the allocation is going to be tiny because you allocated 0, which with libc malloc implementation is going to return you 0x20 bytes as the minimum allocation. So your buffer is going to be tiny, but you're still going to read a lot of bytes to it, so you have a heap overflow. All right. Any questions on this or on the homework in general? Yeah.
So when I was looking at this, my intuition was we don't actually know anything about malloc. Wow. So it might not be calling malloc. We have an invalid 3.
Yeah, I'm not sure why I called this mymalloc instead of malloc. But kind of just everything should kind of just like make sense based on the names, I would say, or just kind of just heap allocation. This is kind of a gets an integer. If this was a question you had, I hope you asked it on CamSwire. But yeah, this was kind of supposed to like represent some allocation routine there. Could have maybe been made a bit clearer by just calling it malloc. I'm not sure why it wasn't, but yeah. Okay, that's pretty much it for today's lecture then. And for homework 4, there is a reading up on Moodle. The reading is fairly heavy, so make sure you get started on it early, not the last day. I think the homework itself shouldn't take that long, but the reading might take a little to process.
Discord added more